So thank you to the organizers of this workshop and conference. So my name is Ashley Ruiter. I'm faculty at the University of New South Wales. I'm going to actually demask because I did my COVID test this morning and it was negative, in Canberra, Australia. So I'm going to talk about white dwarf mergers that lead to things other than type 1a supernovae. So normally I work on binary evolution population synthesis, trying to figure out which evolutionary channels might lead to something that could explode as a type 1a supernova. And so Jan showed this same figure earlier today. I'm just showing sort of a mini smorgasbord version of the different evolutionary channels you can sort of get leading to transients involving white dwarfs, namely type 1as. So I'm going to focus more on binaries involving white dwarfs that would be on the lower mass end. So not the things that Maxime talked about that might lead to creation of neutron stars and not type 1as, but other things that would lead to hydrogen deficient carbon stars. And so I know this is a lot of text, so I'm also going to focus on the first 2 points. So just briefly on what kind of things might double white dwarf mergers make. So I think we all kind of know that there's a whole lot of different things that can happen through the merger of two white dwarfs. So just loosely, depending on what the masses of those things are, at the lower mass end, so involving helium-rich white dwarf mergers, you would more likely get something like subdwarfs. So so SDB stars, SDO stars, possibly extreme helium stars. And then going a little bit more massive, of course, you can make something called R Coronae Borealis stars, of which we, a decade or so ago, we didn't know of that many, but now we know of about maybe 150 of these in the Milky Way, as well as the Magellanic Clouds. And so I'll talk a little bit about those soon. It's also plausible that you might get some type of thermonuclear transients at the sort of so-called medium mass range when you talk about white dwarf mergers. Higher mass ranges on the order of 0.8 or so solar masses, when you have the two stars each about that range, you get possibly type 1a supernovae, right? So I won't talk about type 1as much. There's going to be a lot of talks during this week on type 1as. I have a short review on the different progenitor channels in a 2020 paper I gave for an IAU symposium just before the pandemic. And then of course you have the higher mass range white dwarf mergers that could lead to something more exotic, possibly the formation of a neutron star, which we heard about a little bit earlier in this afternoon. Okay, so what are hydrogen deficient carbon stars in the first place? So this is sort of a very general category. So technically they encompass anything from, that's basically hydrogen poor. So hydrogen stars, you could include Wolf-Rayets, but in this instance, the hydrogen deficient carbon stars, or the HDCs, have an underabundance of hydrogen and an overabundance of carbon, okay? And in this particular case, so the most commonly known sort of category of these HDC stars are the R-core bores, right? And so these are thought to be produced from the merger of two white dwarfs, where one is probably a carbon-oxygen-rich white dwarf, sort of standard white dwarf, and the other one is a helium-rich white dwarf. And just to note again that you can only form these helium-rich white dwarfs through binary evolution. So the universe is not old enough to have produced helium white dwarfs that form from single stars. So a little bit more about these ones. Okay, so R Coronae Borealis, they've been known for a couple centuries now. They have these really irregular, sort of unpredictable, profound changes in luminosity. And they also have radial and non-radial pulsations, but beyond that, they can drop by on the order of 8 or 9 orders of magnitude over the course of a very short period of time. And it's thought that the origin is double white dwarf merger, and in this process, the R-core bore will produce a lot of dust, of carbon-rich dust. And so when we see these dips in the luminosity, we're actually seeing that dust cloud sort of puffing out toward our line of sight. And so these R-core bores are known to be very dusty, and they produce, some of them you can actually see this dust shell around them. Yeah, and they have sort of strange isotopic ratios of hydrogen. So in R-core bores, the 16 to 18 oxygen ratio is on the order of 1, where in the sun you'd expect something like 500. So these are definitely very weird. and thought to originate from mergers. Okay, so there's also another class of hydrogen deficient carbon stars, of these HDCs, of which R-core-Bohrs are just one subclass. There's another class or subclass called the dustless HDC stars. Okay, now up until the 1960s, only 4 of these were known. And then just recently, my colleague Patrick Tisserand discovered like 27 more of these in the galaxy. So this was pretty exciting. So we're working right now. This is really a work in progress. We're trying to really figure out like what make these dustless ones that are they look a little bit like R-core-Bohrs, but they're less luminous. What make the R-core-Bohrs? We know they're probably white dwarf mergers, but what are the masses and what are the compositions of those white dwarfs that lead to these making these objects? So it's the interesting thing, I guess, about these dustless stars. So this is the paper that I think is published now about the discovery of these new dustless systems. Is that we're trying to sort of delineate, well, we have these observations and we're growing the sample of the observational sample of these HDC stars, both R-core-Bohrs and the dustless ones now. What do they come from, right? So I did a little kind of cartoon here to try to see, okay, what might the different white dwarf merger types make, okay, in this context. So let's take out the degenerate ones. So we're only looking at, mergers of all the plausible cases here. So we think that probably when you merge a helium white dwarf with another helium white dwarf, or what I'm going to call a hybrid white dwarf, which is when you have, it's kind of mass-wise in between the CO white dwarf and the helium white carbon-oxygen white dwarf. You basically have carbon-oxygen in the core and a helium-rich mantle. Okay, these hybrids are important to remember. When you have these types of mergers here with the purplish arrows, you might make something that's in the lower mass range, the subdwarf SDB or SDO stars. Of course, there are many channels that could possibly make the subdwarfs. But we think probably the R-core-Bohrs and in general, the hydrogen deficient stars are made through these various channels where you either merge a helium white dwarf with a carbon-oxygen white dwarf, or a hybrid helium-carbon white dwarf with something else, either helium-rich or carbon-oxygen white dwarf, okay? Now I'm not including the, I'm not really gonna, I said I wouldn't talk about 1As, so I'll skip that. But it turns out that when you sort of combine all these different possibilities together, it's a little bit confusing because you see different configurations can plausibly be responsible for many different things. So part of why I wanted to come to this conference and in general the workshop is to talk a little more to observers, but also people working on theory, about, how can we work to delineate the different progenitors, right? These mergers clearly exist. We have over 100 million double white dwarfs in our galaxy alone. Most of these will never interact, but those that do will do something. So, yeah, here's a little plot. So Ken Shen, I believe, has a very similar one to this, sort of showing you in the mass space of the more massive white dwarf versus the less massive white dwarf. If you merge these together, what are the plausible things that might come out of this, right? So this plot's a little bit old right now, but you get the right idea. You can get, this is kind of the region here that I'm talking about, our Corona Borealis phase in terms of the masses. Okay, normal 1As, you need higher mass. So these R-core-Bohr stars, they do have a spatial distribution that's mostly centered around the galactic bulge. So they're typically from an older population, although we do see some of these in the large and the small Magellanic clouds as well. Similar for the dustless ones that were recently discovered, there are less of these. We see them also mostly centered around the bulge, some in the halo as well. So they're clearly mostly coming from an old population. So a little bit, so I tried to sort of look at this with my population synthesis modeling and see, okay, well, which channels can we plausibly maybe describe these different HDC stars based on, what we know about them from observations. It's still not even clear if the classical R-core-Bohr stars are actually from the same progenitor channel as the ones without the dust, or if they're from two distinct populations. So in short, so I'll just cut to the chase here. I ran some population synthesis modeling So on the x-axis, you see the total mass of merger. So this is 0.9 here. So merging two white dwarfs with a total mass of 0.9. These are just model number on the y-axis, so not normalized to the galaxy or anything else. It turns out that based on where we think the mass distribution of our core bores lies, so that's around 0.9-ish solar masses, mergers of these hybrid helium, carbon, oxygen white dwarfs with CO white dwarfs seem to most readily explain this population. I won't go into, feel free to talk to me about this later. I sort of lumped all the other channels together. Clearly the other channels do something, maybe make the dustless ones, some of them make subdwarfs. In this instance though, in the syntax I've written, it's important to note that it says HYB CO and not the other way around. It really matters which white dwarf was more massive. So in this progenitor channel, it actually is the initially more massive star in that binary on the ZAMs that turns into this hybrid white dwarf. And then it's the less massive the star that's less massive on the ZAMs that turns into the CO white dwarf. That gives you the correct mass distribution. If you flip it the other way around, you don't get the same distribution. It lies somewhere in that orange histogram. Yeah, so this is the channel that we think probably is responsible for the R core bores and maybe some fraction of the dustless ones. One other thing I just want to briefly show are delay time distributions of these R core bores, right? So as I showed before, a lot of these hydrogen deficient stars are centered around the bulge, some are in the halo, so they're generally old, but we do see some in the Magellanic clouds. Now it turns out from this channel I just showed here, the blue histogram, there's a bimodal delay time distribution. Okay, they come from two different channels. Some have very long delay times on the average, 8 gigayears or something like this. So these would be, sort of matching, I suppose, the population we might see in the bulge. And then you also have a set of younger systems that happen less than 2 gigayears, and these could possibly be the ones that we're maybe seeing now in the LMC and in the disk. Yeah, so I think, let me see, I just wanted to show this. This is kind of if I deconvolve all those different channels, you can see all the, sorry, it's a bit hard to see the different colors, but you can see it's the hybrid CO ones that stand out. We have a lot of these. Roughly the numbers work out to what we would expect in terms of the rate of our core bore formation in the galaxy, assuming these things last for about 10 to the 5 years, which their phase is expected to last about that long. And I had a summary slide. There it was. Yeah, so yeah, that's basically all I wanted to mention. So we think that, but this is still a work in progress. But plausibly the channel to maybe explain these R core bores is this hybrid plus CO white dwarf merger channel. We're following some of these systems up with high resolution spectrograph, the Valache spectrograph at the AAT in New South Wales, Australia, to get some more surface abundance information. But yeah, I think I'm just about out of time. I'll just end with a nice cartoon of a typical evolutionary channel leading to one of these mergers. And you can see there's only one common envelope that happens here. So thank you.
Questions? Okay, the one in the back. Yep.
Hi, Ashley. I'm Sumit.
Hi.
So in your DTD plot, there's a gap between 2 to 4 gigayears, I think.
Yes.
Yeah. Is that real? Like the stars, they're not producing.
It's real in my data. Yeah. So basically, okay. So the main difference between these is, so the long delay time systems, they undergo a common envelope phase. So this is way before the R core bore merger, right? They undergo the common envelope phase when the star is on the AGB, so it's really large. Whereas the short delay time ones, they go through the common envelope phase, and there's only one. Mostly have only one common envelope phase. When they're red giants, so much smaller. So that's why you get the strong bimodality, just the different size of the star.
I see. And are the amplitude, is that like higher than like what's predicted from the single double degenerate channels?
From the single and double degenerate.
Or let's just say double degenerate. Is
Oh,
that, yeah. Like between 0 and 2.
no, it's not higher.
Okay.
Because the most common type of white dwarf formed is the carbon-oxygen, right? And so actually we expect a larger number of double CO white dwarf mergers than any of, so yeah, I didn't actually show any of the CO-CO mergers on my plots. I just kept everything lower mass. The CO-CO mergers would be larger in amplitude in terms of rates, yeah.
Any other? Oh, one more question here.
Hi, I'm Valeria from MPA, and I really like the fact that you showed that you see these binaries in both Milky Way and Magellanic Cloud.
Mm-hmm.
And I think it's like a sort of magical situation for any theorist studying populations, right? Because you have a Milky Way old population
Mm-hmm.
and a young population formed in a very different metallicity. So I wonder what like information you can extract from there, maybe like the relative numbers or things like that can tell you something interesting.
Yeah, no, thank you for that question. I mean, that's exactly my own question as well. I'm hoping, so yeah, we'd like to follow these up. So far we've only really tried to follow up with more detailed spectroscopy, some of the ones in the galaxy. And of course it depends on time of year. And we actually had 5 nights on this spectrograph and only like 20% of one night we got some data. Like it was just terrible La Nina weather in Australia right now. But yeah, it would be really, I also looked a little bit on how this changes with metallicity. But I mean, it doesn't change too much, but yeah, hopefully I'll have more to say about that in the coming year or two, something like that. Yeah.
There.
Oh, is it okay? Right. So hopefully this is a fast question, but maybe not. What is it that favors in your modeling the hybrid white dwarfs versus helium white dwarf binaries for making the arc-core-bores?
The masses that come out of it. So that's an interesting question though, because I was actually chatting with Philip Podrzadlowski last week, and we were talking about arc-core-bores a little bit, and we realized, oh, the observational constraints on masses of arc-core-bores, where do they come from? And we kind of realized, oh, we don't really know. They don't seem to exist. So that's why I think I had a quote around one of the masses of arc-core-bores. We don't really know the masses of them. In real life, we only know from population synthesis, but we can extrapolate from what we know about extreme helium stars, which I think it's easier to model them because there's more UV information on these ones. So, but if you just kind of assume the whole, oh, what we've been saying for 20 years, or the masses are the arc-core-bores around 0.8, 0.9, this is matching exactly what we get with the mergers of the hybrid and the CO. The helium and the CO also, you're sometimes more likely you wouldn't merge them. Well, Ken might argue with me there, but so in my model, sometimes you would make something like an AMCBN, you won't necessarily merge because the mass ratio is more skewed.
And here.
Hi, I'm Kevin. So I just had a naive question. I don't do pop synth, but when you just said that we expect that there are many more double CO mergers than other classes because CO white dwarfs are mostly produced. They're mostly produced by single star evolution, but one of the tricky things in binary evolution, I thought, is you need to get the white dwarfs to about a 12-hour period or so for GR to be able to kick in and merge them. Mm-hmm. And that usually involves some kind of interaction event. And so one of the issues is to make a CO white dwarf, you need to have a helium flash at some point, right? You need to start burning helium. And there's an issue of oftentimes you can do that during the first kind of star's evolution. But the problem is then you end up at a shorter period. And when the second star tries to evolve, its red giant branch gets truncated and you end up with not a CO white dwarf. So I'm wondering, is there some obvious channel that besides that suddenly gives you lots of double COs at short periods?
You just have the IMF on your side, I guess. So even though like some of the stars that maybe if they were, you know, living as a single star, they would have made a CO white dwarf, but now because they're in a binary, they would make a hybrid or helium. You just go to higher mass ranges and you still have enough of them, it turns out, to make a large number of CO white dwarf mergers. Yeah.
All right, that's the end of this session. Let's thank all our speakers again.